Welcome to the fourth and final video in our series where we build a TinyGPT model from scratch. In the last video, we opened up the model and watched it turn a batch of token IDs into a probability distribution over the next token. At the start of training, those probabilities are essentially random guesses. The model knows nothing. And the question is, how does it go from knowing nothing to generating something that sounds like it came from an AI textbook? So in this video, we cover three things: how the model measures how wrong it is, how it uses that signal to update itself over thousands of steps, and how we evaluate if it has actually learned something useful. Welcome to Scovia, where we turn AI ideas into everyday intuition. Let's quickly recall where we were. The model receives a batch of input windows. For every token position, it produces a probability distribution over the entire vocabulary, which is its best guess at what comes next. And then we have the targets, which is the actual next tokens from the Y array that we built in video 2. Now, we need to answer the question of how wrong the model is in predicting the next token. That gap between prediction and the truth is what the training process lives on. It measures it, shrinks it, and repeats that process over many, many examples. At the start of the training, the model's weights are all initialized randomly. That means its probability distributions are essentially noise. If the vocabulary has 10,000 tokens, the model might spread that probability nearly evenly across all the possible tokens. The right answer gets maybe a 0.00001% chance, the same as thousands of other wrong answers. Without a way to measure that wrongness and trace it back through the model, nothing really changes. The weights stay random and the outputs also stay noise. What we need is a signal that says, here are all the weights that you can blame, and here's how you can change them. That signal is the loss function. The loss function used in a language model is called cross-entropy loss. And here's the intuition for it. The model produces a probability distribution over all the tokens in the vocabulary, but then we know what the correct next token is. It's sitting in Y, right? So, what cross entropy loss does is it asks how much probability did you assign to the correct answer? If the model gave the correct token a high probability, say 0.9, the loss is low. If it gave the correct token a tiny probability, let's say 0.001, then the loss is high. More precisely, it takes the negative log of the probability that's assigned to the correct token. Log of a number close to 1 is 0, which is low loss, and log of a number that's close to 0 is a large negative number, which is very high loss. So cross-entropy loss rewards confidence in the right answer and punishes confidence in the wrong ones. This is computed at every token position and every window in the batch, then averaged into a single number, which is the loss for that step. Once we have the loss, we need to use it. So the model has millions of weights, right, which are numbers that are inside the embedding table, inside the attention layer, the feed forward network, etc. Each of them has contributed in some small way in producing that wrong answer. Backpropagation is the process of tracing that contribution backwards through the model. It calculates for each weight, if we nudge this number slightly, how much does the loss change? That rate of change is called the gradient. A large gradient means that this weight has a big effect on the loss. A small gradient, on the other hand, is that it barely matters, right? So once we have the gradients, we update every weight in the direction that reduces the loss by a small amount that's controlled by the learning rate. And we keep doing this again and again, thousands of times. Let's watch the full loop in motion. Step 1 is you sample a random batch of windows from the training data. Step 2 is you run the forward pass, so the token IDs go in and the probability distributions come out. Step 3 is where you compute the loss against the targets. And step 4 is where you're running backpropagation to get the gradients. In step 5, you update the model weights using those gradients. And that finishes one tiny training step. TinyGPT runs this loop thousands of times. Early on, the loss is high, the model is just guessing randomly, but after enough steps, the loss drops. The model has started to pick up patterns in the data. The optimizer that handles the weight updates and TinyGPT is called AdamW. You don't need to know the details right now, but the key idea is that it's a smarter version of the basic update rule. This one adapts the step size for each weight individually. As the model trains, the training loss keeps decreasing. But that alone doesn't tell us if the model has learned anything useful, right? A model can cheat by memorizing the training data. So it can get really good at predicting the exact tokens that it has seen before, but it doesn't really generalize well. So it doesn't learn any transferable pattern. That's why we keep the validation set separate. Every few hundred steps, we pause training and evaluate the model on validation data, which has text that the model has never seen before. If the validation loss is dropping along with the training loss, the model is genuinely learning. If the training loss keeps falling but the validation loss starts climbing, then the model is overfitting, which means it's memorizing the training data and not really learning the patterns. For TinyGPT, that is trained on the AI Club textbook, losses should trend downward together because the language and vocabulary are consistent enough across chapters that patterns learned in one section should transfer to another. Loss is the right number to optimize during training, but it's not always the most intuitive number to interpret. A related metric is called perplexity, and it's a little bit easier to reason about. Perplexity is essentially telling you on average how many tokens was the model choosing between in each step. If perplexity is 100, the model is essentially confused between 100 equally likely options at every position. If perplexity is 5, it has narrowed things down to about 5 plausible next tokens. A perfect model would have a perplexity of 1, which means it's always certain about the right answer. So perplexity is just the exponent of the loss, which is e raised to the power of the loss. And as the loss drops during training, perplexity drops as well. For TinyGPT, watching perplexity fall from the hundreds down towards single digits tells you that the model is genuinely learning the structure of the textbook. Once the model has trained for enough steps, we can ask it to generate text. And here's how generation works. We give the model a starting point, which is a few tokens to kick things off, and then the model runs its forward pass and produces a probability distribution over the next token. We sample from that distribution to pick one token. We append that token to the sequence, and then we run the forward pass again on the longer sequence. And then you keep repeating this process one token at a time, like adding one at a time, until we have generated as many tokens as we want. Two parameters control how the model samples at each step. First one is temperature, which scales the logits before applying softmax, which means low temperature makes the distribution sharper, and the model picks the most likely token almost every time, producing a safe, predictable text. If the temperature is high, then that flattens the distribution, and the model takes more risks, producing more surprising and more creative outputs. The second technique is top K. So instead of sampling from the full vocabulary, we restrict the model to only look at the k most likely tokens at each step. top k of 1 always picks the single most likely token, and top k of 40 allows the model to choose from the 40 best candidates weighed by their probability. So here's the takeaway: training a language model is a loop where you predict the next token, measure how wrong you were with cross entropy loss, and then trace that wrongness back to the model with backpropagation and nudge the weights in the right direction. Do that thousands of times on randomly sampled windows of text, and the model gradually learns the patterns in the data. Validation loss tells you whether it's generalizing, and perplexity tells you how uncertain it still is. And the generation part lets you see the results directly, one token at a time, and this is shaped by temperature and top K. So that's TinyGPT and the core of how every modern language model learns. But TinyGPT is still a base language model, not a chat model. Its main objective is simply to continue the text by predicting the next token. Turning a base model into an assistant, like the ones we interact with in chat applications, requires several additional stages. The model must learn how to follow instructions, how to respond to a conversation, and behave safely to produce answers that are more useful to humans. These steps involve techniques such as instruction tuning, preference tuning, and alignment. And we are going to explore each one of them in a future series. I hope you found this series useful. Please subscribe to Scovia for more AI insights, and as always, stay curious.